Some of the most powerful, most mind-bending rules of physics aren't hiding in some fancy lab. Nope, they're all around us, hidden in plain sight. And today, we're going to pull back the curtain on one of these incredible secrets, a fundamental law that connects everything from an Olympic athlete to the shape of our entire galaxy.
It all kicks off with this one simple question. We've all seen it, right? A figure skater starts a spin, arms stretched wide, turning at a pretty graceful speed. But then they pull their arms in tight, and whoosh, they suddenly accelerate into this incredible, dizzying blur. How do they do that? It seriously looks like magic, but I promise you, it's not. It's just pure, beautiful physics.
And what's so cool is that we don't need some quantum supercomputer to crack this case. The answer lies in just one single fundamental property of how our universe works. So you ready? Let's dive in and figure this out together.
Okay, first things first. To solve this riddle, we've got to learn the language of rotation, the physics behind all the things that turn, twist, and twirl.
All right, the main character in our story today is a concept called angular momentum. Now, the simplest way to get your head around it is to just think of it as spin in motion. It's a way to measure not just if something is spinning, but exactly how much spin it has. Now, I know angular momentum might sound a little abstract, but you're actually already familiar with its cousin, linear momentum. That's just the oomph a bowling ball has when it's barreling down the lane. Well, angular momentum is the exact same idea, but for things moving in a circle. It's the oomph of a spin. And here's where it gets really interesting. This spin actually has a direction. Physicists have this super simple trick to figure it out, called the right-hand rule. Seriously, you can try it right now. Take your right hand and curl your fingers in the direction something is spinning. Whichever way your thumb is pointing, that's the direction of the angular momentum. It's a neat little way to visualize this totally invisible force. So, we have our spin in motion, our angular momentum, but that's only one piece of the puzzle. Now we need to talk about rotation's hidden weight. The reason some things are just way harder to get spinning than others. This hidden weight has a name, the moment of inertia. My favorite way to think about it is as an object's rotational laziness. So, if mass is how much an object resists being pushed in a straight line, moment of inertia is how much it resists being spun around. It's stubborn. Now, an object's moment of inertia, its rotational laziness, comes from two things. First, its total mass. Heavier things are harder to spin. But second, and listen up, because this is the absolute key to solving our skater mystery. It depends on how that mass is spread out from the center of the spin. This is where an object's shape becomes everything. Just imagine trying to spin a hula hoop. It's kind of awkward, right? That's because all of its mass is way out on the edge, far from the center, which gives it a really high moment of inertia. Now, picture a solid bowling ball of the same exact weight. It's way easier to spin because its mass is packed in tight and close to the middle. So how the mass is distributed is just as important as how much mass there is to begin with. Okay, we've got our two key players. Angular momentum, the spin in motion, and moment of inertia, the rotational laziness. Let's put them together and finally reveal the unbreakable law of spin that solves this whole thing. The law itself is just beautifully simple. It basically says this: if you have a spinning system and nothing from the outside messes with it, no pushing, no pulling, no friction, then the total amount of spin in that system has to stay exactly the same. Always. It can't be created out of nowhere, and it can't just disappear. This is one of the absolute cornerstones of physics, the law of conservation of angular momentum. So, when our figure skater is spinning on the ice, for that moment, she's basically a closed system. If we ignore that tiny little bit of friction from her skates, her total amount of spin, her angular momentum, must be conserved. It has to stay constant. So, let's think about that total spin. It's basically a product of two things: the object's rotational weight, that's the moment of inertia, multiplied by its rotational speed. These two things are locked together, like they're on a cosmic seesaw, always trying to stay in balance. And here it is, the big aha moment. Since the skater's total spin has to stay constant, if she changes one side of that seesaw, the other side must change to balance it out. So by pulling her arms in, she's yanking all that mass closer to her center. This dramatically lowers her rotational weight, her moment of inertia. And because the total spin can't change, her rotational speed has to shoot through the roof to make up for it. It's not magic at all. It's just a perfect demonstration of physics in action. So now that we've totally cracked the skater puzzle, let's zoom way, way out. Because this law doesn't just apply to people on ice skates. It literally shapes everything, from the tiniest atoms to the largest galaxies. I mean, this law is absolutely everywhere. It's why a high diver tucks into a tight ball to flip faster. It's what keeps planets locked in their orbits around the sun. It's even the reason our solar system is a flat disk. The giant cloud of gas and dust that it formed from had a tiny, slow spin. As gravity pulled all that stuff inward, its moment of inertia shrank, so it had to spin faster and flatten out, exactly like our skater pulling in her arms. And you know, all this spinning isn't just about motion. It's also about energy. When you see a ball rolling down a hill, its total kinetic energy is actually a combination of two things: the energy of it moving forward and the energy of its own spin.
Think about it for a second. The skater has to do real work to get her spin started in the first place. And when she pulls her arms in, that energy doesn't just vanish, it gets converted directly into that incredible blazing speed. Rotation is a really powerful way that our universe stores and releases energy.
So it's just amazing, right? A single, unbreakable rule connects a skater's pirouette to the majestic swirl of a distant galaxy. And it kind of makes you wonder, what other incredible hidden laws are out there quietly shaping our entire universe right here in front of our eyes?